Everybody, it's Mrs. Harbin. We're looking at video notes 2.3, playing a song from Nirvana. You might be able to figure out while I'm playing it. It has to do with the periodic table. Make sure you can do these 4 things when we're done, or by the time we do the unit test. So, we've been talking about the periodic table. Make sure you do section 6.3. There's some questions at the end that you're going to have to answer from that chapter. Look at the pictures. They will help you. They will help you. Alright, so here we go. The first trend in the periodic table we're going to look at is atomic size. What's another word for saying atomic size? We're talking about the radius. Not how heavy they are, but if you go from the center of an atom, from its nucleus, to its outermost electrons, that's the radius of the atom. How do you measure that? Well, you really have to have 2 atoms bonded together, and if you can measure the distance between the nuclei, half of that is the radius. Okay, so make sure you know this is what atomic radius means. This is the way it's measured. Half the distance between the nuclei of atoms in a diatomic molecule is the radius. Okay, so what is the trend in radius? Well, look at this picture. Take a mental picture of it. What do you notice happens to the atoms as you go down the periodic table? Okay, what happens to the atoms as you go across? So let's do get smaller going across. That's a periodic trend. The periodic trend is that atoms get smaller going across in their radius. Well, let's talk about why. Okay, so as I go from here to 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 here, we're getting more protons. As you get more protons, you're not changing the energy level that the electrons are in, so the stronger nucleus pulls the electrons in closer. Okay, because more protons going across, stronger pull of nucleus on electrons pulls them in closer. Alright, so here's the trend, smaller going across. Here's why. That's how we explain it. That's a periodic trend because it's going across the table. What about the group trend? That one, bigger going down, bigger going down, bigger going down, bigger going down. So atoms get bigger going down a group. Okay, so this is the group trend. Why? Because more electrons. Okay, so I'll just put it this way. Electrons are go into higher energy level. Okay, so this is the first energy level, second, third, fourth. So as I go from period 3 to period 4, the electrons have to go into a higher energy level, and core electrons, that's all the electrons that are already there, shield the outer electrons from pool of nucleus. So we explain it with what's called the shielding effect. All the core electrons, and then you try to put a new electron in at higher energy level, it's going to be farther away. Okay, atoms get bigger going down, smaller going across in their atomic size. Okay, here are just the representative elements. So this is the whole periodic table. These are just group 1A through 8A. Notice the trend, smaller going across, bigger going down. Take a mental picture of this, and then if you can see the atoms, it's going to help you explain all of the other trends. So please memorize the trend in atomic size. Now we're going to talk about a different trend. This trend, definition time, is in electronegativity. So you're saying, wow, that's a big word. What does electronegativity mean? Electronegativity, definition, write it down, write this, write it down, write this. Okay, electronegativity is the ability to attract electrons. So one atom is attracting electrons when it's making a bond. Okay, so guess what? It only works for elements that make bonds. The trend, fluorine is the what's up in electronegativity. Fluorine is the electronegativity master. It's the one with the highest electronegativity. Francium is not. So where are they on the periodic table? Fluorine's over here, francium over here. Okay, this is the highest electronegativity, this is the lowest. So let's explain why. Why can fluorine have an ability to attract electrons in a bond? Fluorine is the smallest in its period, okay, And since it's a small atom, its nucleus is not that far away from any electrons it's trying to bond with. Okay, so it'll be easy to attract electrons to make a bond. Right? All right, so fluorine is small, so we're redefining the trend based on, so electronegativity depends on the size of an atom. Okay, strong nucleus, small atom, pull bonded electrons towards itself, high electronegativity. Okay, so let's talk about francium then. Francium, big atom. Okay, so this big atom, if it wants to pull electrons from another element to make a bond, then it can't pull electrons really strongly, because any electrons it's trying to pull are far away from its nucleus. So francium has low electronegativity. Fluorine has high electronegativity. Okay, so the bigger an atom is, the less electronegative it is. So if we got this, atoms get bigger going down, atoms get less electronegative going down. Atoms get smaller going across, atoms get more electronegative going across. All right, another trend, another property, ionization energy. See that word ion? That means a charged particle by losing or gaining electrons. Okay, so when we talk about ionization energy, here's the definition. It's the amount of energy needed to remove an outer electron from an atom. So we're talking about, how do you make a positive ion, cation? Okay, so for instance, we have sodium atoms, 11 protons, 11 electrons. How much energy does it take to take away one of those electrons? That's the ionization energy. Okay, after one electron goes away, then it's a positive ion, cation. Okay, so the amount of energy it takes to take away one electron is called the ionization energy. What's the group trend? Okay, ionization energy gets easier or lower going down a family. Why? So what happens to the size of atoms going down a family? Right? Atoms get bigger. Okay, that means this electron that's trying to be removed is far away from the nucleus, so it gets easier to take electrons away from bigger atoms. Okay, so atoms get bigger going down, so it means it takes less energy to ionize them going down a group. Sorry. So what happens in a period? Okay, well, what happens to atoms in a period? They get smaller. The smaller it is, the harder it is to take away its outer electrons. So ionization energy increases across a period. Why? As the radius gets smaller, elements are more able to, the electrons are strongly connected to the nucleus, so it takes more energy to remove them. Okay, so ionization energy is the amount of energy it takes to remove an electron. Okay, big atoms, less energy, small atoms, more energy. That's what I want you to remember. Okay, so we're moving on. We're talking about valence electrons when we first talk about ionization energy. All right, it's kind of easy to take outer electrons from an atom because they're on the outermost energy levels. Okay, but then if you try to take electrons that aren't valence, then it takes more energy to remove electrons that are more strongly held towards the nucleus. All right. So what if we try to take one electron, then another one, then another one? That's called successive ionization energies. One, and then another, and then another. First electron for magnesium, it takes 738 kilojoules. If you try to take a second electron from that magnesium ion, it takes 1,450. You try to take a third electron, it takes, whoa, look at the difference. This is about double. This is huge. A huge difference trying to take the second electron and then the third electron. That's huge difference, right? Why? Well, magnesium is group 2A, so it has two outer electrons. All right, so let's just say in its outer energy level has two outer electrons. Take the first one, all right, not bad. Take the second one, not bad. You try to take a third electron, you're trying to take it out of the core electrons for magnesium. All right, so each electron takes different amounts of energy to remove, but when there's a huge gap between one electron and taking the next one, then you're probably going from valence to core. Okay, so explain the main way atoms different, and you just explain everything. So what is it? It's about atomic size. Bigger atoms are less attractive because the outer electrons are so far away from the nucleus. Right? Nuclear attraction. More protons means more nuclear attraction. So we can explain stuff in terms of atomic size. Ionic radius, new trend. The size of the ion. This is comparing the size of an ion to the size of an atom. Okay, so when you have an atom, It's neutral. It's got all of its protons and electrons. Right? When you have an ion, if you have a cation, then an outer electron is removed. What happens when you take something away? It gets smaller than it was originally. All right, so this is smaller than that one. Why? Cations get smaller. Removing electrons makes them smaller. All right, it's kind of like onions, right? Ogres have layers, so do onions. You take away the first layer, outer electron, then the onion's a little smaller after that. Okay, don't cry. All right, anions get bigger, so you start a neutral atom, and then you add an electron. It becomes negatively charged. Well, you add something, it gets bigger. Look, this snake, you add another. This is a neutral atom or snake. You add another electron, it's bigger. You add 2 electrons, it's bigger. Okay, adding electrons makes bigger compared to not atoms. Okay. All right. So all we have to talk about next is valence electrons are being the outermost electrons. 1A, 1 valence electron. 2A, 2 valence electrons. 3A, 3 valence electrons. 8A, 8 valence electrons. So 7, 6, 5, 4. These are the amount of outer electrons is the same as the A group. It's a trend in periodic. 1 through 8. 1 through 8. Periodically repeating. 1 through 8. Alright, so metals and nonmetals react differently. Metals are losers, and they become positively charged cations. Nonmetals are gainers, they become negative. What's the best metal reactor? Well, the biggest unattractive loser. So here we have metals, right? And this is the biggest one. Okay, so metals get bigger going down and over. Okay, based on this. So big metal over here. Francium is the biggest metal there is. It's unattractive to other electrons because its outer electrons are so far away, so it's easy to lose. So best metal reactor, big because outer electrons far from nucleus. Okay. Unattractive because big atoms, harder to pull electrons in. Okay, so that's for metals. Bigger metals, more reactive. Non-metals, smaller metals are attractive stealers. Okay, small because stronger nucleus, pull electrons in close, electrons in. Attractive because filling outer shell, easier when small. Okay, we'll keep talking about it. I want you to think about the lab we did for that one. Okay, so most reactive on the periodic table. Here's our zigzag line to talk about reactivity. These don't react. Fluorine. Non-metals go to fluorine, most reactive. Winner, chicken dinner. Okay, metals, the biggest metals are most reactive. So this way. Winner. Francium is the metal winner, biggest loser. Fluorine is the non-metal winner, small is the gainer. Okay, noble gases don't react because they have full valence shells. They have 8. 8 is great for the most part. Okay, to review, we'll play this song again. There are group trends, periodic trends, up and down. Okay. Up and down is a group trend. Across is a periodic trend. If you know atomic size, it explains everything else. Metals are losers, but it's a positive thing. Well, make cations. Quiz yourself. Quiz me. Quiz your lunch table. Now, here are the 2 questions you need to answer from the book, okay? Page 177, checkpoint, and number 23, page 178. Good luck with that. See if you can do this. All right? Same group, same properties. Similar, okay? Metals are losers. Atomic radius is a big one, and then you can explain the rest of them. So good luck with that, and peace out.